First, for introduction, stingless bee honey. Stingless bee or Meliponidae is one of the bee species that can produce honey and play an important role in flower pollination. Honey produced by stingless bee is known with various names such as Meliponidae honey, stingless bee honey, pot honey, and in Malaysia it is called as kelulup honey. Honey spoilage is the main problem in storing stingless bee honey as it has high water content. To overcome this problem, it was necessary to reduce the water content through dewatering process. However, honey generally not sensitive to the heat. Therefore, the dewatering process should be consumed at lower temperature. Low temperature vacuum drying is widely used to reduce the water content from heat-sensitive materials such as honey. Vacuum conditions enable moisture of the material to be removed at lower temperature. There have various types of low temperature vacuum drying available, such as microwave vacuum drying, freeze drying, vacuum evaporation, vacuum drying, and spray drying. However, this method unable to meet requirements for dewatering stingless bee honey. Low temperature vacuum drying with induced nucleate boiling has been developed to meet the dewatering requirement as it is able to reduce the water content of honey without damage its nutrient content. Nucleate boiling is a process in which bubble nucleates grow and depart from the heated surface as shown in figure 1. The performance of low temperature vacuum drying with induced nucleate boiling could be affected by temperature. Therefore, the objective of this study is to investigate the effect of temperature on the dewatering rate of stingless bee honey. For material and method, Figure 2 shows the experimental setup and Figure 3 shows the schematic diagram of experimental setup. The experimental setup has been developed to dewatering 200 grams of honey. 200 grams of honey sample was placed in a pressure vessel that was connected with a vacuum pump to create vacuum condition. Pressure gauge was used to monitor the pressure inside the vessel. A stainless steel inside the vessel was used as a heating element that transferred heat to the honey sample. Water inside the water tank was heated until obtaining the required temperature, and water pump was used to allow hot water flow from water tank to stainless steel inside the vessel. The temperature inlet, outlet, and honey were monitored by using a thermocouple. 3 different temperatures were conducted, which were 40, 45, and 50 degrees Celsius, to investigate the effect of temperature on the dewatering rate of honey. The pressure was set at -96 kPa for every experiment. The initial and final water content of honey was measured by using the digital refractometer. The honey sample was dewatered for 5 minutes and the process was repeated 3 times for each temperature. The dewatering rate of honey was calculated by using this formula, which is a dewatering rate equal to changes in water content divided by time taken for the dewatering process. For result and discussion, Figure 4 shows the average water content of stingless bee honey after the dewatering process, and Figure 5 shows the dewatering rate for each dewatering temperature. The highest reduction of water content was at 50 degrees Celsius, which was reduced from 26.5% to 25.1%. As the result, it obtained the highest dewatering rate, which was 0.28% per minute, while the lowest reduction of water content and dewatering rate was at temperature 40 degrees Celsius, which was only reduced by 0.7% from initial water content, and the dewatering rate was 0.14% per minute. The dewatering at temperature 45 degrees Celsius was able to reduce from 26.5% to 25.8% water content after 5 minutes, and the dewatering rate was around 0.16% per minute. The water content decreased faster at higher temperatures due to the increases in temperature difference between the sample and the heating element. Figure 6 shows the dewatering rate from the present study and other methods. As shown in the figure, the dehumidifier invented by patient show the lowest dewatering rate, which is approximately 0.00033% per minute. This method can reduce 0.6% water content of 57 tons of honey in 30 hours. Dewatered reduce the water content of honey with low pressure vacuum, and the dewatering rate was about 0.044% per minute at 68 degrees Celsius. And low temperature vacuum drying with induced nucleate boiling by Wormley et al. Able to reduce the water content at the rate of 0.2% per minute at 45 degrees Celsius, which is 5 times faster than the dewatering rate achieved by Dewatered. The dewatering rate from the present study with the same dewatering temperature was around 0.22% per minute. Microwave vacuum drying showed the fastest drying method compared to others, as the dewatering rate of this method is around 2.56% per minute. However, this method cannot be considered as the best method because the radiation emitted from the microwave has potential to damage the nutrient and quality of honey. For conclusion, the performance of low temperature vacuum drying with induced nucleate boiling increases as the dewatering temperature increases from the range of 40 degrees Celsius to 50 degrees Celsius. The final water content of honey was decreased. The highest dewatering rate was at temperature 50 degrees Celsius, but this temperature is not suitable for heating honey because it could overshoot and exceed the temperature limit for heating honey. Dewatering honey at temperature 45 degrees Celsius was highly recommended to minimize the deterioration of honey quality during the dewatering process.